Welcome to the AI and GIS Frontier podcast. Let's get into today's topic.
Today we are diving into large language models for geospatial analysis. What we are seeing is LLMs, the same technology behind ChatGPT and similar tools, being adapted to understand spatial concepts, generate GIS code, and act as natural language interfaces to geospatial workflows. It is fundamentally changing who can do spatial analysis and how fast they can do it.
Let us make this concrete for GIS professionals. How would someone actually encounter this in their workflow?
Picture this. You are a forest analyst, and you need to calculate timber volume estimates across 100 different stands using LiDAR-derived canopy height models. Normally, you would write a Python script or build a model builder workflow in ArcGIS. With an LLM-powered GIS assistant, you type in plain English. Calculate timber volume for each stand polygon using the canopy height raster, apply the regional allometric equations, and export the results to a geo database. The system generates the Python code, executes it, and hands you the results. A tool called GIS Copilot, integrated with QGIS, has demonstrated an 86% success rate on multi-step spatial tasks like this.
86% is impressive. Tell us more about GIS Copilot.
GIS Copilot is an autonomous GIS agent that sits inside QGIS. You give it a natural language instruction, and it figures out the sequence of geoprocessing operations needed, writes the code, and runs it. For forestry work, that means tasks like clip this harvest boundary to the riparian buffer zone, calculate the area, and flag any blocks that overlap with spotted owl habitat. Instead of clicking through 5 dialog boxes, you describe what you want, and it happens. State and federal GIS staff have been testing it for generating zoning maps and analyzing land use changes.
There is also a specialized model called BBGeoGPT. What makes that different?
BBGeoGPT is fascinating because it was built by fine-tuning the open-source LLMA2 model specifically for geospatial tasks. In testing, it achieved 32% higher accuracy than GPT-4 on geospatial problem-solving. That matters because it shows that a smaller, specialized model can outperform a general-purpose giant when it comes to understanding spatial relationships, coordinate systems, and GIS operations. For a forestry agency that cannot send sensitive land management data to a cloud-based commercial API, having an open-source model you can run locally is a game-changer.
How are researchers benchmarking these capabilities?
There is a new benchmark called GeoAnalyst Bench with 50 real-world Python geoprocessing tasks. These are not toy problems. They include things like watershed delineation, viewshed analysis, spatial joins across mismatched coordinate reference systems, and multi-temporal change detection. The benchmark evaluates whether the LLM generates a valid workflow, whether the code structure matches best practices, and whether the output is actually correct. It is giving us a realistic picture of where these models excel and where they still struggle.
Where do they still struggle?
Edge cases in coordinate transformations are a big one. The models sometimes get confused when data spans multiple UTM zones, or when you need to handle vertical datums for elevation data. Complex topology operations can also trip them up. And there is a real risk of the model generating code that looks correct but produces subtly wrong results, like calculating area in a geographic coordinate system instead of a projected one. For forestry applications where timber volume calculations have financial implications, you absolutely need a human reviewing the output.
Let us talk about the bigger vision. There is research on large spatial models. What is that about?
Large spatial models, or LSMs, are the next frontier. The idea is to build billion-parameter models that can accept and generate multimodal geospatial data, raster, vector, and text, all in one system. Think of it like this. You upload a Sentinel-2 image, a shapefile of forest management units, and a text description of what you need, and the model understands all 3 inputs natively. It could generate a land cover map, a written report, and a vector dataset of change polygons, all from one prompt. We are not there yet, but the research agenda is actively being developed at Penn State and other institutions.
For an environmental consultant using GIS daily, what should they be doing right now to prepare for this shift?
3 things. First, start experimenting with the natural language GIS tools that already exist. The ArcGIS AI assistants, the QGIS GIS Copilot, even just using ChatGPT to write your geoprocessing scripts. Get comfortable with the interaction pattern. Second, learn to be a good editor. These tools will draft your analysis, but you need to verify the logic. Knowing your GIS fundamentals actually becomes more important, not less, because you need to catch when the AI gets something wrong. Third, Think about what analyses you have been putting off because they were too tedious. Multi-step environmental impact assessments, cumulative effects analyses across hundreds of forestry cut blocks, watershed-scale riparian buffer compliance checks. Those are exactly the kind of tasks where LLM-powered GIS will save you days of work.
That is practical advice. It sounds like the role of a GIS analyst is evolving from someone who executes workflows to someone who designs and validates them.
Exactly right. The value shifts from knowing which buttons to click to knowing which questions to ask and whether the answers make sense. That is a much more interesting job, frankly, and it means GIS professionals who understand their domain deeply, whether that is forestry, hydrology, or urban planning, become even more valuable, not less.